Hi, and welcome to Allen High School's discussion of acid and base chemistry at the APIB 1 level. We are in the midst of discussing the pH that comes from 0.023 molar solutions of strong and weak acids and bases. So we are on right now our weak base, and we know it's a weak base because we have a Kb here. Now we did not add volume to volume, so we don't have a dilution. We have no stoichiometry because all we have is weak, and stoichiometry is for soluble salts, strong acids, strong bases, and then whenever we add an acid to a base. So we're going to jump right now into our equilibrium here. We have no other source of ammonium ion, like we don't have ammonium nitrate or ammonium chloride. All we have is the ammonium that arises when the ammonia takes an H+ from water and no base. Now, we don't know how far it's going to go. I'm going to use a B for base because that's my constant reminder. If I have B, that means it's going to be 2 steps to pH. I often had students stop a step early. For one, it was illogical, and two, it ended up being wrong. Since I started doing this, I get much less of that. If you're solving for B, you're solving for hydroxide, and that's going to be 2 steps. So this is 0.023 minus B. We're going to neglect this to simplify our math. It's borderline, honestly, in this problem, but we're going to go ahead and run with that. If you did your check of 100 times K, our number in front is still bigger, but not much bigger. Okay, so KB is going to be our products, NH4+, times our hydroxide over reactants, NH3. So I have 1.8 times 10 to the minus 5th is equal to B squared over 0.023. Now, once we're done solving that, B, which remember is equal not to H+, but to our hydroxide, is 6.434 times 10 to the minus 4th. All right, and I'm going to take the log of that, and when I take the log of that, that's not pH, that's POH. Remember that little p in front means take minus the log of whatever follows. So for example, you may see pKb, and that means take minus the log of the Kb value. So we've got 0.434 times 10 to the minus 4th, and I get 3.19. Now, it wouldn't be logical to stop here. It asked us for pH, and we expect our pH to be greater than 7 because we have a base. Yes, it's a weak base, but it's still a base. To get our pH, we have to do one more step, 14 minus 3.19, and I get, for my pH for this, 10.81. which indeed is a fairly basic. Okay, that's relatively concentrated. All right. Now, the other thing that it asked us for is what is the percent ionization? The percent ionization is the part that reacted divided by the initial amount. So in our case, what we would have is that our percent, and I'm running out of room, so I'm going to have to erase a little bit of this. I hope you've captured that information already. Okay, so get some room. Let's do our percent ionization, and we expect it to be much less than 100 because that's the definition of weak. So my percent ionization is going to be B, the amount that reacted, 6.434 times 10 to the minus 4th, over my initial amount. I want to know what part of this initial reacted, times 100, and I get for that 2.8%. Now, I want to caution you here, the reason we don't have tables of percent ionization is percent ionization will vary with the starting amount. Whereas K, remember, is independent of your starting amount of product, and that's why we do it based on that law of mass action or K value. Now, I want to very quickly, we can go pretty quickly on this next one because the calculation's nearly identical for acetic acid. In fact, the Kb of ammonia is the same as the Ka for acetic acid. Again, we did not add volume to volume since all we have is a weak acid. You know that because you've memorized your strong acids, and it also gives us a Ka. So we're going to jump right into our equilibrium. Since I started with the same values, it's the exact same setup that we saw. Whoops, I'm going to use A here, not B. Okay, got carried away. 0.023 minus, Dina, did you see what I did? I was talking too fast. This should just be minus A, right? So I want you to fix that. I'm so sorry about that. So this is minus A. There we go, all fixed. Oh, Dina. Okay, so Ka is equal to our products, H3O plus. Make sure you know how to do this. You will typically be asked explicitly for this on an AP question. So you need to know how to write an equilibrium constant. What's nice about acid and base equilibria is we always deal with one H plus at a time. So you'll always have 1-to-1 mole ratios. It makes it a little simpler in that sense. All right, so I have 1.8 times 10 to the minus fifth is A squared over 0.023. A is equal to 6.434 times 10 to the minus fourth molar. Now remember, this time that's equal to our H plus. And if you take minus the log of that number, we get a pH equal to 3.19. You would also get your percent ionization equal to 2.8%. And that would be if we took the part that reacted divided by the starting amount times 100. Now, one last comment before I leave you here. I want you to be really careful that you don't mix up the terminology strong acid versus weak acid and concentrated versus dilute. Now, in our examples, we had the exact same concentration of strong and weak. So it would be expected that the pH of your strong acid would be less than the pH of your weak acid because our H plus concentration is greater for the weak and the strong. But that's only because they were the same initial molarity. All right, the same molarity initial. It is possible, and so you've got to be very careful. Don't make generalizations. It's possible to have a concentrated weak acid have a pH that's lower than a dilute strong acid. So be a little careful with that terminology. Okay, until I see you in class, this is signing off.